Okay, for question 15, it says a metal worker wants to make an open box from a sheet of metal by cutting equal squares from each corner as shown. And it says to write an expression for the length, width, and the height. Well, if he's cutting out squares, equal squares, that are measuring, because they're squares, they have equal sides, and the sides here are represented by a length of x units. So, therefore, our height is simply going to be x, which makes our length, if you look at our length, is 16. You get rid of this x on this side, and this x on this side would be equal to 16 minus 2x, or negative 2x plus 16. And the width, the same, would be 12 minus 2x. So that's part A of the question. Part B, it says use your answer from part A to write a function for volume. Volume is length times width times height. So length, 16 minus 2x times width, 12 minus 2x times the height. X, we'll leave it in factored form. That's the function for volume. For part C, it says to graph the function and find the maximum volume that can be contained by the box and the size of the square cut that produces this volume. So what we need to do is we need to take this and put it in our graphing calculators. We're going to put it in factor form, so we'll come here to y equals. And clear this out, and we have the quantity 16 minus 2x times the quantity 12 minus 2x times x. Okay, we're going to zoom standard, and we're going to take a look at this. We probably won't be able to see the max as we do, so maybe we'll try zoom fit. I don't know how well this is going to work. Oh, not good at all. So what I'll do is I'll come and I'll change my window for the x min. Remember, x is representing length, so it can't be negative. So we'll just say 0. As far as the maximum value of x, think about it. 6 minus 2x. If it's anything bigger than 8, that would give us, actually for 12 minus 2x, anything bigger than 6 would give us a negative width. So we'll say an x max of 6. The y, again, as far as the volume goes, I'm not really sure. We can't have a negative volume, so we'll say 0, and we'll go up to 100. Then we'll graph this. Ooh, the volume's going to be much bigger than this. But we do see that we have our domain correct, so what we're going to do is we'll go back to window. We'll come here to y. Now we just need to be able to see it. We'll count by 100. Now when we take a look at this graph, wow, that's way too big. Even though we just need to be able to see it, that's just way too much. So I don't know. It looks like if we're counting by 100, 500 should do it. Let's not count by 100 anymore. Let's count by 10. So now when we graph it, that gives us a little better picture. And it says we want to find the maximum volume. So we go to second, calc, maximum, left bound, we need to get to the left of that max. And there we are on the left. Enter. Right bound. Let's get back to the right. Should be okay there. Guess, as long as it doesn't give us an error, we're all right. And the maximum volume apparently is approximately 194.1 inches cubed. And the ideal dimension for the size of this square would be approximately 2.27 inches. And that's how you answer question 15, parts A, B, and C.